Hi Eleanor, this is Dan DeBrow, and I just wanted to show you how to complete this problem that you asked me about earlier today. So right here is our picture of the situation with a plank and two rollers. And what I've done is I've drawn the free body diagram for the plank and the rollers. And these are, as we talked about earlier, that the plank has a force given to the right, 5.80 newtons, and two frictional forces from the between the plank and the rollers pointing to the left. And then we also talked about the rollers themselves having two frictional forces, one from the plank on top and one from the ground on bottom. And also, as we discussed, both of these forces must point to the right in order to satisfy Newton's third law for the plank, and in order for friction to make sense for the ground. So the key to understanding this problem is that we have a system of equations, but also we have rolling without slipping. And so first, let me set up the force equations, and then we'll talk about how to continue. So for the plank, we have that the net force is equal to ma in the x direction, and this turns into the given force minus 2 times the frictional force is equal to the mass of the plank times the acceleration of the plank. Then we can look at one roller, and applying F net equals ma to a roller, we get F plank plus F ground equals mass of the roller times acceleration of the roller. Finally, and I should keep it here, we will do torque for the roller. So this is forces, and this is torque for the roller. So we have torque net equals I alpha. And so even though we are given the radius r, it turns out that we're not going to need it. So here's what happens. We have Fp minus Fg all times r is equal to I, which is 1/2 m r squared, times alpha, which is a roller over r. Okay, so let me circle the three equations that we have here, and it seems that we have a problem that we have four unknowns, and it appears that the unknowns are as stated here: the two accelerations and the two forces of friction. Now, the key to solving this problem is understanding that the motion is rolling without slipping. And what that means is that if we look carefully at a roller, the point of rotation for the roller is the point of contact with the ground instantaneously. Okay? And that means that even though each roller is rotating on its axis, it is also accelerating forwards. And you may recall that if we were to describe the velocity of the center of mass of the roller as vcm, the velocity at the bottom of the roller would be 0, and the velocity at the top would be 2 times the velocity of center of mass. And this is the fact that rolling without slipping is rotational motion with something pinned down, so velocities look like this. Okay, so this is just pure rotation plus pure translation, where all points are moving with the same speed. And so, if this is v center of mass, and this is v center of mass, and this is v center of mass, I'm just doing a mini review here, then we add these two together to get that the top is moving with twice the center of mass velocity, the center is moving with 1 time the center of mass velocity, and the bottom is moving with 0 velocity instantaneously. And that's what defines rolling without slipping. Now, how does that apply to this problem and acceleration? So now what we realize is that acceleration is the derivative of velocity with respect to time. So we can think about this that basically if the velocity is 0 at the bottom, then a is equal to 0 at the bottom. And if we call the acceleration ap for the plank at the top, so in other words, the plank as a solid object is translating with the same acceleration everywhere, that means that the plank has an acceleration of ap and the top of the roller will be accelerating with the linear acceleration of ap, which means that the center of mass of the roller is ap over 2 at the center of mass. In other words, the key to solving this problem is understanding that the center of mass acceleration of the roller is half the acceleration of the plank. Once we have this, this is a fourth equation, and everything else turns into numbers at this point. So I'm going to go ahead and quickly solve through the rest of this. I'm going to take this third equation down here and rewrite it. So what I'm going to have is that the force of the plank minus the force with the ground is equal to, now I have to do a replacement. Instead of AR, I'm going to write AP over 2. So I'm going to get 1/4 MAP. So that's one equation we're going to use. We are also going to use our second equation, unaltered. Okay, well, there is an alteration. The alteration here is that originally we said FP plus FG equals MAR, but that's also AP over 2. So that's where this half comes from. And if we simply add those equations together, we get that 2 FP is equal to 3/4 MAP. Then we realize that F minus 2 friction plank equals MA plank. So we'll write that F minus 2 friction plank equals MA plank. Simply add those together and we get F is equal to 3/4 M plus big M all times the acceleration of the plank. Now we plug in the numbers that were given here to solve for F, and I'll put in the numbers that you gave me. So F is 5.80 newtons, and this is 3/4 times 2 kilograms plus 5.10 kilograms, and this gives us a repeating decimal, but just to round it, it's 0.879 meters per second squared. Okay, so that is the acceleration of the plank. The acceleration of the roller is simply the acceleration of the plank over 2, so it is approximately 0.439 meters per second squared. Finally, we can solve for the two forces of friction. Okay, we can bring the acceleration of the plank up to here to get that friction of the plank is equal to 3/8 M A plank, and that's 3/8 times 2 times 0.879. So the friction between the plank and the roller is equal to 0.659 newtons. And finally, we can go one step back to here to say that friction with the ground is equal to 1/2 MA plank minus friction plank. So that's 1/2 2.879 minus 0.659, and that is approximately 0.220 newtons. And so again, this is F plank and this is F friction over here. And so this does it. Everything else is as we discussed, and we have the correct directions for all of the forces in our free body diagrams, and we found what we needed to. So I think, again, the big thing to understand here is that because we have rolling without slipping, this relationship is important. So there you go.